So, in this lecture, we will talk about weak interactions in nuclei and particles. And so, in the first couple of slides, we have examples of weak interactions. So, for example, you have beta decay. This is an example of a weak interaction in a nucleus because you can have, let's say, beta minus emission, beta plus emission, and electron capture. So, these are of course spontaneous decays which occur in the nuclei where such processes are possible. For instance, examples are given here. Carbon 14, for instance, can decay into nitrogen 14 plus a beta minus and an anti-electron neutrino. Boron 8 can go to beryllium 8, emit a beta plus, a positron, and a electron type of neutrino. Similarly, beryllium 7 can capture a K-shell electron, also it can capture an L-shell with smaller probability, and go to lithium 7 plus a electron type of neutrino. Okay. So, for instance, the decay corresponding to the K-shell electron capture gives rise to a monoenergetic neutrino. The L-shell capture gives rise to a different energy, but again single energy neutrino, a sharp line. So, were you to detect these neutrinos, you would get lines corresponding to K-shell capture and to L-shell capture. Okay, then there are also weak nuclear reactions that take place. For instance, the very first reaction that is part of the PP chain that powers the sun, so this is a fusion reaction, but this is not a strong fusion reaction in the sense that there is a beta plus and a neutrino involved in that. So, this is a weak process and is fortunate because since this process goes through the weak interaction, it's rather slow, the cross section is very small, and that leads to a very slow burning sun which enables it to live for as long as a few, it will probably live another 5 billion years more at least. And so, were this to be an electromagnetic or a strong interaction, it would have died in the course of seconds or minutes or hours. Okay. So, this is crucial for our existence, for life to evolve. It takes billions of years for life to evolve. And so, this is the fact that this is a weak process is extremely important in leading to life on Earth, let's say. The other place where the weak interactions are important is that you have the wrong parity, that means parity violating admixtures in nuclear wave functions. Now, the strong interactions respect parity, so called parity quantum is a good quantum number, but you can have the opposite parity states in a predominantly certain parity state. So, if you have a positive parity, then you have a predominantly positive parity, and then you can have admixtures of the order of 10 to the minus 10, 12 and so on of the wrong parity. So, for instance, the oxygen 16 8.87 MeV excitation energy 2 minus state decays by alpha to carbon 12 with a very tiny weight of the order of 10 to the minus 10 electron volts, although the excitation energy is so high that this should have been a few MeV wide. Okay, so this is 10 to the what 16 times or so smaller than what it should have been, and this is because of the parity violating admixture in the wave function. Okay, now this is also important in decays of particles, the fundamental particles as well as composite particles such as the pion and so on. An example is given here of the leptonic weak decays where a lepton, a heavier lepton decays, and in this case the mu minus decays to electron type of neutrino and the muon neutrino. Similarly, the tau lepton, the tau minus decays to electron and two more neutrinos, the nu tau and the nu e. Actually, this should be a nu bar e. because you have an electron which is a lepton, that's an anti-lepton to conserve lepton number. Similarly, in this case, again, there is a mistake here. There should have been maybe the bar has migrated somewhere else. It may be at the wrong place somewhere. It may have got deleted. Okay, so you have the tau decaying to a mu minus also, and a nu mu bar and a nu tau. You can have hadronic, sort of semi-leptonic weak decay, in which you have a pion, let's say, which is a meson, and then that decays to a mu plus a nu mu. Okay, so these are leptons, but this is not a lepton. This is a hadron, so this you can call it semi-leptonic decays. However, you can have a decay into which doesn't have any leptons at all. For instance, for a free hyperon, which is a strange baryon, that can decay into a neutron and a pi zero, but through the weak interaction process. It can also decay to proton plus pi minus, and since this is a weak decay, then it actually goes through at a very small rate, and its lifetime is of the order of 10 to the minus 10 seconds, a few times that, and so on. When the lambda is bound in a nucleus, and that can happen, you can actually create lambda nuclei. Then, of course, your the final state, which has a nucleon here, that has to go to an unoccupied orbital, and so it can live a little longer in a nucleus. So, because you have to take into account the Pauli blocking in the final state. Similarly, a K0, a kaon, neutral kaon, can decay into pi plus, pi minus, and a pi zero. So, you have 3 pions in the final state and a kaon in the initial state. So, this is again goes through the weak interaction, and therefore, it has a relatively long lifetime of the order of I think it's about 10 nanosecond, or of the order of 10 nanosecond or so. And this is a strangeness non-conserving weak process. So, the weak process can of course violate strangeness, strong processes cannot. They obey strangeness conservation, bottomness, topness, and whatnot. But weak processes can violate that. Okay, so let's look at first nuclear beta decay. Now, in nuclear beta decay, what was observed was a continuous electron energy spectrum, and that was figured out by Wolfgang Pauli, as he proposed that there is a third body there, which is the neutrino. He called it a neutron in those days, but then later it came to be known as the neutrino, the small particle, by Amaldi. It was named by Amaldi, but then Fermi used the same name in his seminal paper on the weak interaction, the beta decay process. Okay, so the energetics of this is that the Q value of course has to be positive if this beta decay has to take place, and so in the case of beta minus decay, MA of Z has to be greater than MAZ plus 1, because when a beta is emitted, then you have to conserve electric charge, this has to go to Z plus 1. Similarly, Q beta plus not only has this, actually the sum of these two have to be positive, because the Z has one more electron than Z minus 1. So, to account for that, then there's a 2mc squared that comes in. And so, this Q beta plus, if this has to be positive, then this decay can in principle at least go through from the energetics point of view. Then this is the condition that MAZ minus 1 minus this minus 2mc squared, this has to be positive. Similarly, in the case of electron capture decay, MAZ has to be greater than MAZ minus 1. Okay. So, now for instance, if this Q beta value is greater than 1 MeV, then you have both such possibilities. You can have beta plus emission, but you can also have electron capture. Okay. Both are allowed. But if the Q value is less than 1 MeV, which is roughly twice the rest mass energy of the electron, then of course you only have electron capture. You cannot have beta plus because the mass difference is smaller than 1 MeV. Okay, so these are typical electron and positron spectra, and in this case is 64 copper. It's an odd nucleus, so it can go to an even nucleus on the proton rich side or the neutron rich side, and the beta spectrum was actually measured quite early, even before the discovery of the neutrino. And this is from a paper by Ellis and Wooster in the Proceedings of the Royal Society in 1927. So 3 years before Pauli proposed the neutrino. So what was seen was a continuous energy spectrum all the way up to the end point. Of course, in another, this was, I think, in, let me see, I don't remember, this is a radium E, I think. From copper 6, so this is radium E, not copper 64, but these two spectra are in the case of copper 64, so the E minus spectrum and the E plus spectrum, and the x-axis is of course normalized to the maximum value that it can have in that particular decay. So it's 0 to 1 basically. Now you can see that in this normalized momentum or the momentum spectrum, the peak occurs slightly on the higher side as compared to the beta minus. The beta plus peak appears slightly higher than the beta minus peak in this, of course, normalized spectrum, because the Q values are slightly different for these two decays. And this can be attributed to the effect of the Coulomb distortion on the electron or positron. Okay. So this can be the probability for decay or the decay rate dWi from initial state to final state can be written down as a matrix element of the weak Hamiltonian between the initial and final state with phase space factors, and you can go through this algebra. This is there in any of the standard textbooks, and this is actually proportional to the momentum, the energy of the electron, and Q minus E whole squared. Okay. So, and in a particular energy interval. So, dW by dE is proportional to PE, EE and Q minus E whole squared. So, if one uses plane waves, then of course what you actually need is a additional factor called the Fermi function Fz of E, where Coulomb effects are taken into account. Coulomb effects meaning the final state is affected by the Coulomb field of the daughter nucleus, and this Fz takes into account that effect. So it is actually a function of both the charge on the nucleus as well as the final state, the daughter nucleus charge, as well as the energy of the electron. The effect is less for higher energies, effect is more for higher Z. So the effect of how it pushes it relative to one another we saw in the earlier slide. Of course, the endpoint remains the same. That's a constant, and that is Q minus m nu c squared. So, of course, if m nu is 0, then this is just the endpoint is just Q value. Otherwise, it is Q minus m nu squared. Okay, so in the non-relativistic limit, when the velocity of the electron is much smaller than c, then this Fermi function can actually be approximated by x by 1 minus e to the minus x, where x is just plus or minus this number here, 2 pi alpha times zc by ve for beta minus plus decay. So this x is positive for beta minus decay and is negative for beta plus decay. Alpha is of course the usual fine structure constant, 1 by 137 approximately, and c is the velocity of light, ve is the velocity of the electron. So one can see that this dW, the partial probability, decay probability, vanishes at E, the electron energy to be 0. So you can go back to the earlier slide. So here it's proportional to E and Q minus E. Okay, so it is 0 both in the beginning of the spectrum and at the end of the spectrum. Now, quite often you will see spectra where at 0 energy you have a finite contribution. That means when you plot the probability that you see a certain number of events in an energy bin, then however fine that bin may be, you might still have a finite number at E equal to 0. But that is because of the finite energy resolution of the detector that you use. Any detector that you use will be non-ideal, and therefore it will have a certain spread in energy. So the higher energy electrons actually come in a lower energy bin, and so the spectrum will actually start at a finite value, not 0, at E equal to 0. Okay, E measured equal to 0. Okay, so also another thing to note is that for Q value much greater than the rest mass of the electron, then it peaks at about half the value of Q. Okay, peaks at Q by 2. Similarly, the last term there depends on the neutrino mass. And, okay, we can again go back to this expression and this factor here. So this depends on the mass of the neutrino. Okay. So if mass is 0, of course, the last term is just 1, and then you can actually compute this. You can integrate this over the energy, and then for beta decay, you find that the rate at which it decays goes like Q to the 5, fifth power of the Q value. Similarly, you can get the T half as logarithm 2 by WIF, and it will turn out that this is 1 by f of ZQ times a constant divided by the square of the matrix element, mf squared plus mgt, because you can have both Fermi and Gamow-Teller contribution. We will come to what the Fermi and Gamow-Teller contributions are. In any case, the ft value is actually some constant divided by this mf gt whole squared. So this is a number, and so for we'll see how that changes with allowed decays and forbidden decays and so on, with different values of forbiddenness. Okay, now just an aside. So since there is a Q value to beta decay, and the three-body state of course involves a neutrino, which will of course escape any system that you have which contains this beta decaying nucleus. But the electron of course can get stopped in that in the whatever is the material around the beta decaying source. And so suppose you have a reactor, a nuclear reactor. So suppose let's assume that it shuts down. Okay, then the total number of betas per fission is about 3. One can sort of see this. This is a fairly good estimate per fission fragment. And then there are 2 fission fragments. Because why so many decays? Because the fission fragments are neutron rich, and so when they beta decay, they will come down to the stable nuclei, and then you will get an emission of roughly 3 betas per fission and 2 fission fragments. So you get 6 per fission. So you get 6 betas per fission. The mean energy of the beta is of the order of 1 MeV. So the total energy release is about 6 MeV. And so now you can compute that if you have a reactor which is undergoing the fission, then there are so many fissions per second taking place, and each fission process contributes about 200 MeV to each of the fission or to both those fission fragments. And you can see that this is a relatively small number, but not negligible, because this is about 3% of the total power production that takes place from a reactor. So suppose you have a 1 gigawatt electrical reactor, you have 3 gigawatt thermal, 3000 megawatt in when it is working at full capacity. Now, to start with, as soon as the reactor shuts off, you have something like 3% of that, which means about 90 megawatt that is being produced as a result of the beta decays. And so this is the heat generation that takes place. Of course, these are typically short-lived. So what happens is that the beta activity decays, and then only the long-lived ones survive. So you have time scales ranging from a second to a year and so on. So when you have to consider the year half-lives, then of course the amount of heat generated per unit time is small. But initially you can have, as I said, as much as about 90 megawatt heat produced, and then this decays with time. And this is important, and as we saw in the accident that took place in the Fukushima reactor a few years back, That was, I think, about 15 years ago, 10 to 15 years ago. Okay. So, the beta spectrum, as I said, if you suitably plot it, WPE divided by PE squared times this FZ if E, and take the square root of that, and then plot it versus this E, then this should come down, and it comes down to 0 at the Q value. Okay. However, if the neutrino has a finite mass, then so this is what is plotted here versus the electron energy. So if it has a finite mass, then instead of this straight line here ending at the Q value, it will end at Q minus m nu squared. Not only that, the slope of this curve, of this plot, will be infinite at this energy Q minus m nu squared. So this fact is made use of in the detection of finite mass neutrinos. Of course, if you have a resolution, you need a resolution which is slight of the order of, or maybe even slightly better than m nu squared, if you want to actually see this infinite slope. Usually, I mean, this is perhaps would have been possible if you have a neutrino mass which is large, like maybe 20 electron volts or something. But now that we have pushed this upper bound to fractions of an electron volt, we don't have detectors of this resolution. So what happens in practice, if you have a finite resolution, then this plot goes down and has a sort of finite extent like this. So this dashed plot is for zero mass neutrinos, and the dark line is for finite mass neutrinos. So this is the difference that you actually are looking for. Now, if you want to actually measure the mass of the neutrino, you have to, of course, concentrate on this, the end, the spectrum near the end point. Not only that, you have to take cases where the fractional decay in this region is substantial as compared to the full decay, and so you need a small Q value. We saw that the Q values range right from electron volts or keVs to 10, 15 MeV and so on. So it is good to take those cases, of course allowed cases, where the Q value is small, and tritium is a very nice example of that. Tritium, so this is hydrogen, the heavier cousin of deuterium. It has 3 nucleons, 2 neutrons and 1 proton, and then that beta decays to helium-3. This has a Q value of only about 19 keV, and it has a long half-life. So once you make this source, you can look at it for time of the order of years, and so this is one of the favorites for experiments which look for the finite mass of the neutrino. So the differential energy spectrum is given by this, some constant depending on the Fermi function, etc., and then P times EE and Q minus E times the summation of this is the the probability that you have actually a electron that is emitted, which is a leptonic eigenstate, and that may not be a mass eigenstate. So this takes care of that factor. So you start out with the electron type of neutrino, but the electron is actually composed of 3 mass eigenstates. So in principle, it's a summation of these 3 mass eigenstates, Q minus E squared minus M squared, and the square root of that times, of course, this probability factor, amplitude squared. So we already know what is F E of Z and Q, and this is, as I said, the amplitude. So you have to take the square of the amplitude, and M nu is the ith neutrino mass eigenstate. So this is a spectrum which you will see with a finite energy resolution, and if you do the same plot, blow up this part of the spectrum, then for m nu equal to 1 electron volt, this is the blue line that you get, and if m nu is 0, then of course you get this red line. Okay, m nu equal to 0, that's the red line. The blue line is for 1 electron volt, and the total number of counts you expect if you have m nu equal to 0, for instance, is only less than is of the order of 2 into 10 to the minus 13 of the whole spectrum. So you can see that you require very strong sources if you want to get a finite number of counts here, and so this just illustrates that fact. Of course, if it is smaller than this, then this blue line would come closer to the red line, and you would require even more statistics. You would require to count for longer and focus only on this region to look for possible finite neutrino masses. By the way, this is taken from the Katrine website. As of today, this is the best and the most sensitive experiment for a finite neutrino mass. They can actually measure, they are sensitive to 0.2 electron volt by c squared, and they can measure it if it is about 0.4 electron volt by c squared with some reasonable accuracy. Okay, so there were experiments in the 90s and early 2000s. The Russian group from Troitsk, and the other was a German group from Mainz, and they both put bounds of the order of 2.2 electron volts at 95% confidence level, and then they collaborated to build one experiment at Karlsruhe, and that was called the Katrine experiment. Okay, so this Katrine experiment has there is a talk in 2025, and maybe this will be updated this year sometime, that the upper bound for the neutrino mass, actually it should be the anti-neutrino mass, is of the order of 0.45 electron volt at 90% confidence level. Okay, this was reported in a seminar by Catherine Valerius. There's another completely different way of measuring the neutrino. If you knew, let's say, a pulsed strong source of neutrinos, indeed that happens to be supernova. Supernovas emit about 99% of their energy through neutrinos, and this did take place in 1987A. This was observed by terrestrial detectors. In fact, the Kamioka detector measured it, but there are also other proton decay experiments that measured these neutrinos. And if you can model how the supernova explosion takes place, then you can look for differences in the time of flight from photons to neutrinos. So this method was used, and this also gives mass bounds of the order of a few electron volts, okay, between 5 and 10 electron volt by c squared. Okay, so now we come to another kind of measurement, the helicity of the electron neutrino. Now the helicity is defined like this: sigma nu, the spin times the momentum, dot product with the momentum. This is, as you can see, a pseudoscalar, and then divided by the expectation values of each of these operators. And if parity were conserved, this would be exactly 0, but as we know, parity is violated in weak interactions and indeed in beta decay. So this turns out to be a non-zero number. And there is a beautiful experiment carried out by Goldhaber, Grodzin, Sanyar, and reported in 1958, soon after the possibility that parity is violated in beta decay was proposed by Li and Yang. And they used this case, which is absolutely unique. There is no such case in the nuclear table, nuclear isotope table. So the idea is that you actually transfer what you observe from the neutrino. The neutrino you cannot observe directly. You look at the subsequent decay of this, and you look at the subsequent decay in samarium, the photon, which is the 1 minus to 0 minus transition. You look at that, and of course it also decays to the 2 plus state. So you look for this decay, and you look for the circular polarization of this photon. So from the polarization of the helicity of the neutrino, you have got a polarization of the 1 minus state in samarium, and if you see this is polarized, then you can infer back and say that the neutrino was polarized as well. It so happens that this decay scheme is especially lucky for this measurement, because you use nuclear resonance fluorescence. So I think I talked about nuclear resonance fluorescence a few lectures away, and it so happens that the Q value is such that the 1 minus to 0 plus transition involves a 963 keV photon, which is very close to the photon to the neutrino energy. So in electron capture, the neutrino energy is of this order. The other favorable circumstance is that the lifetime of this excited state, the 1 minus state, is a fraction of a picosecond, 0.03 picosecond. And since stopping times are of the order of a picosecond, it means that the photon is actually emitted by a moving nucleus. So there is a Doppler shift to that, and you can of course see it in such a way that the shift is in the right direction, and so you can have resonance scattering from samarium nucleus. Okay, so this chance circumstance that the energy of the photon is close to that of the energy of the neutrino, and also the fact that the lifetime is small, enables you to actually measure the helicity of the neutrino by measuring the helicity of the photon. So this is the paper that they wrote, helicity of the neutrinos. You can see that what they basically say is that you have transferred the measurement of the helicity of the neutrino to measuring the helicity of the photon. And the schematic of the apparatus is, this is from their paper. You have a europium source, and this is in the middle of a iron yoke which is magnetized by this analyzing magnet. So you can flip the current in this in the coils here, and so you can flip the magnetization of the iron, and therefore the last electrons spin can be flipped from up to down, and so the Compton's the elastic scattering of the photons that are emitted after electron capture decay, they can scatter differently, because in principle the elastic Compton scattering depends on the polarization of the electrons that scatter it, and then these fall on a samarium target, and you can have resonance absorption on the samarium target, resonance scattering actually, and then these resonantly scattered photons are actually detected in this. The direct photons are absorbed in this thick lead, and so this is the spectrum that you see, the photon spectrum. You see this 840 keV transition and then the 960 keV transition. So you actually have cycles where the magnet is polarized first in one direction, then in the other direction, and then you look at the count rates, and then they are different, and that is what was measured. The difference in count rates for the magnetization in one direction as opposed to the other direction compared to the average, and this was measured to be about 1.7% plus minus 0.3%. Using this, they determined that the circular polarization of the gamma ray is quite high. It's about minus 66 plus minus 15%. So this is about an error which is about 1/4 of what is measured, and so they concluded that the helicity of the neutrino is -1 plus minus 0.2. Okay. Other measurements which involve beta minus decay, slightly more indirect, they have shown also that the helicity of the anti-neutrino is +1 within error bars. Okay. So, and as I already said, the non-zero helicity indicates parity violation, but this was the first direct measurement of the helicity of the neutrino, a beautiful measurement. Of course, we saw again in an earlier lecture that Madame Wu measured the beta asymmetry in the decay of cobalt 60 by actually polarizing this nucleus and then looking for the asymmetry, and then similarly the electron asymmetry from muon decay was observed by Lederman in an accelerator based experiment. Okay, so analogous to the electromagnetic interaction, Fermi in 1934 modeled the weak interaction Hamiltonian as a current-current interaction. Just as in the case of the electromagnetic interaction, when you have two charged particles, you have currents corresponding to each of them, and then there is a photon current. So there is a charged particle current and there is a photon current. You have a J dot A kind of interaction Hamiltonian. Similarly, here you have a interaction from the hadrons or leptons, as the case may be, and leptons. So electron going to a neutrino or vice versa, and so you have you have two currents in this case also, and this is modeled on the electromagnetic interaction. So for beta decay, the nucleon current is the neutron-proton part, and the leptonic current arises from the electron and the neutrino. At low energies, the nucleonic part has in general contributions from a vector part, which is the Fermi part, and the axial vector part, which is the Gamow-Teller part, with these operators GV times tau plus minus. The tau plus minus are the isospin raising or lowering operators. So you can, if you raise the operator, then you go beta decay one way, and T tau minus beta decay the other way. So you have positron and beta minus, beta plus and beta minus emission. In the case of the axial vector, you have also a sigma tau operator, because you can have a spin flip. You can have a nucleon which, let's say, neutron goes to a proton, but it also flips its spin. So that can be done with the help of a sigma operator. Now, since strong interactions respect parity, then the nuclear wave function, so the initial and final states, they actually have good parity with very tiny admixtures of the wrong parity components. On the other hand, the electron neutrino, of course, they do not exhibit good parity, and so that's how you get the V minus A interaction, and so the leptonic current actually doesn't respect parity, but the hadronic part does. Now, in the allowed decays, you can write down the electron neutrino wave functions as EIKR, but since KR for all practical purposes is very close to 0, you can approximate these by just one unity operator. So the selection rules for the Fermi and Gamow-Teller transitions. In the Fermi case, delta J equal to 0, delta T equal to 0, but the Ti 0 to Tf0 is forbidden, because that, of course, it so happens that the Klipsch coordinate for this is 0. But the delta Tz is minus plus 1 for beta minus beta plus decay, and there is no parity change. In the Gamow-Teller, delta J can be 0 or 1, because the sigma operator has angular momentum 1, it carries angular momentum 1. So you can have both 0 and 1, but again 0 to 0 is forbidden. Okay. In this case, we just say that delta T equal to 0 is Ti Tf equal to 0 is forbidden, but J 0 to 0 is allowed in the Fermi case. It is not allowed in the case of Gamow-Teller, because the operator has a angular momentum 1, so that is not allowed. Now, in the delta T case, you can have both 0 as well as 1, but again initial and final state being 0, that is forbidden. This, of course, means it's the same nucleus. Sorry, this is not the same nucleus. You can have a different nucleus, but T equal to 0 is forbidden. So you can have let's say something which goes from 1 to 0, spin 1 to spin 0, or 0 to spin 1. But if both of them have T equal to 0, then of course this is forbidden. This can, of course, happen in so-called isobaric analog states. One of them is the isobaric analog states of the other. Delta Tz is minus plus 1, similar to this, and again there is no parity change. Now, the forbidden beta decays are the one where delta J is L or L plus minus 1, and the parity change is minus to the power of L. So, in super allowed decays, for instance, in the case of Fermi, then there is absolutely no change in the spin. There is a 0 plus to 0 plus decay, and the log Ft values you can compute from that other expression that we had are between about 3 and 3.5. The allowed transitions, of course, again 0 and 1. So you can have a Gamow-Teller or a Fermi transition. These are other quantum numbers. Delta pi, no, and the log Ft can be between 3 and 10. First forbidden, where you have, let's say, L equal to 1, then you can have delta J equal to 0, 1, 2, and the log Ft's are between 5 and 19. Similarly, second forbidden L equal to 2, then this is like this, and so on. Okay. So this is again taken from the reference here, Wong's textbook on nuclear physics, Introduction to Nuclear Physics. Okay, so in summary, we have seen some of the weak interaction processes. We have discussed the beta decay in particular the energy spectrum, mass measurements of the electron type of neutrino, and the measurement of helicity of the neutrino. Thank you.